The vastness of the universe has always fascinated humanity. Our ancestors gazed at the night sky, awestruck by the millions of stars twinkling in the distance. But those stars are just the beginning of something far larger, far more mysterious. What lies beyond them? What is the true fate of everything that exists within this infinite expanse? The answers to these questions have eluded us for centuries. And yet, despite the overwhelming size and complexity of the cosmos, we are driven by an insatiable curiosity to understand it, to comprehend where everything is headed. In the beginning, the universe was an unknowable entity, a place of gods and myths. The stars were seen as beacons of divine power, and the movements of the heavens were interpreted through the lens of superstition and religion. But with the advent of science, our understanding of the cosmos has evolved dramatically. We have learned that the universe is not just a vast, empty space but a dynamic system with its own laws and rhythms, one that has been expanding ever since the Big Bang. Yet, even with all that we have learned, one question remains at the forefront of our minds: where is everything in the universe really heading? The simple answer is that no one knows for certain. But that uncertainty only makes the question more compelling. In recent years, breakthroughs in astronomy and cosmology have brought us closer to understanding the trajectory of the universe, but many mysteries remain. One of the most profound mysteries is the fate of the universe itself. For centuries, philosophers and scientists have speculated about what will happen when the universe reaches its final chapter. Will it continue to expand forever, growing colder and emptier with each passing eon? Or will it eventually collapse back in on itself, leading to a catastrophic Big Crunch? Some theories suggest that the universe will rip apart, torn asunder by the very forces that govern its expansion. These various theories paint a picture of a universe that is not static, but constantly in flux, moving toward an uncertain future. But how do we even begin to understand the future of such a vast and complex system? The answer lies in the fundamental laws of physics. From the moment of the Big Bang, the universe has been governed by these laws of gravity, thermodynamics, and quantum mechanics, that dictate the behavior of everything from the smallest subatomic particles to the largest galaxies. And yet, despite our deep understanding of these forces, there are still aspects of the universe that remain beyond our grasp. One of the most compelling theories about the future of the universe is the concept of an ever-expanding cosmos. This theory was first proposed by astronomer Edwin Hubble in the early 20th century, when he observed that galaxies were moving away from us at great speeds. This observation led to the conclusion that the universe is not static, but constantly growing, with galaxies receding from each other as the fabric of space itself stretches. The implications of this discovery are both awe-inspiring and unsettling. If the universe continues to expand indefinitely, it would mean that galaxies, stars, and even entire solar systems will eventually drift far enough apart that they can no longer interact with each other. This could lead to a universe that is cold, dark, and lifeless, with no stars or galaxies left to light up the night sky. In this scenario, the universe would continue to expand at an ever-increasing rate, gradually losing all its energy and becoming a desolate, frozen wasteland. Yet, despite the chilling nature of this theory, it is not the only possibility. Some scientists have proposed that the universe could eventually experience a Big Crunch, a scenario in which the expansion of the universe slows down and reverses, causing all matter and energy to collapse back in on itself. This theory suggests that the universe could undergo a dramatic and violent implosion, ending in a singularity where the laws of physics as we know them cease to function. The concept of the Big Crunch raises fascinating questions about the nature of time, space, and matter. If the universe were to collapse, what would happen to all the stars, planets, and galaxies that populate it? Would everything simply cease to exist, or would it be reborn in some new form? In addition to these possibilities, there is another theory that suggests the universe could ultimately experience a big rip. In this scenario, the expansion of the universe accelerates so rapidly that it overcomes the gravitational forces holding everything together. This would lead to the eventual tearing apart of galaxies, stars, planets, and even atoms themselves, disintegrating everything in its path. The idea of the Big Rip is both terrifying and fascinating, as it suggests a universe so unstable that it will eventually tear itself apart. The forces driving this expansion, mysterious and largely unseen, are known as dark energy, and they play a central role in shaping the universe's destiny. Yet, despite their importance, we know very little about dark energy, and this unknown factor only deepens the mystery of the universe's fate. So, where does all this leave us? We are left with more questions than answers. Will the universe expand forever, growing colder and emptier with time? Will it collapse back in on itself in a cataclysmic event? Or will it be torn apart by forces beyond our comprehension? The truth is that we do not yet know the answer. And perhaps that is the most compelling part of this cosmic mystery, the uncertainty, the unanswered questions, and the endless possibilities that lie ahead. As we venture further into the unknown, we are reminded that the universe is not just a scientific puzzle to be solved. It is a place of wonder, mystery, and awe. Each new discovery brings us closer to understanding our place in the cosmos, but it also reminds us how little we truly know. And that, in itself, is both humbling and exhilarating. For in the vastness of the universe, there is always more to discover, always more to learn, and always more questions to ask. In the end, the true fate of the universe may be beyond our comprehension. But that does not mean we should stop asking the question. For it is in the asking, in the pursuit of knowledge, that we find meaning, purpose, and connection to the cosmos around us. Whether we ever uncover the answers to the universe's most profound mysteries or not, the journey itself will continue to inspire us, provoke us, and leave us in awe of the incredible, mysterious universe we call home. In the early 20th century, a discovery fundamentally altered our understanding of the cosmos. Edwin Hubble, an American astronomer, observed something extraordinary. Galaxies, once thought to be stationary and fixed in place, were actually moving away from us. This revelation would forever change our perception of the universe, introducing the concept that space itself is expanding. The idea that the universe is not a static, eternal entity but a dynamic, ever-growing system set the stage for much of modern cosmology. The implications of this discovery are far-reaching. Imagine for a moment the universe as a balloon. If you were to place dots on the surface of the balloon and then blow air into it, you would see those dots move farther and farther apart from each other. This is a simplified analogy of what Hubble observed in the cosmos. The galaxies, each containing billions of stars and planets, are like those dots. And as the universe expands, the galaxies are carried away from one another, just as the dots on the balloon's surface are carried apart by the balloon's inflation. But the discovery of the expanding universe raises an even deeper, more philosophical question. Where is everything in the universe really heading? In many ways, this question is as old as humanity itself, echoing our quest to understand our place in the vastness of the cosmos. While Hubble's observation was groundbreaking, it only added to the mystery rather than providing an answer. If the universe is expanding, where is it expanding to? Is there an end, or will it go on forever, stretching farther and farther until all matter is dispersed into nothingness? This question would set cosmologists and physicists on a search for answers, one that would unfold over decades. If the universe is expanding, then it must have had a beginning, a moment when it was compacted into an incredibly small, dense state. This would lead to the theory of the Big Bang, an event that marked the birth of space, time, and all the matter that would come to populate the universe. The implications of this theory are profound. If the universe had a beginning, does it also have an end? As scientists peered deeper into the universe, they began to realize that the expansion was not slowing down as they had once expected. In fact, it was accelerating. Something they discovered was pushing the galaxies apart at an increasing rate. This mysterious force, which no one could explain at the time, was later dubbed dark energy. Its existence is one of the great unsolved mysteries of modern physics. Dark energy makes up about 70% of the universe, yet it remains invisible and undetectable. The very force that is driving the universe's expansion is, in essence, a ghostly enigma. The idea that the universe is expanding, and that this expansion is accelerating, creates a sense of urgency about its ultimate fate. If the acceleration continues indefinitely, the universe will stretch further apart, galaxies will be driven into isolation, and stars will burn out, one by one. This scenario, known as the Big Freeze, suggests that the universe will continue to expand forever, growing colder and emptier with each passing billion years. It paints a picture of a universe gradually succumbing to entropy, with all matter and energy spread so thin that life, if it exists anywhere else in the cosmos, would cease to be possible. In this chilling vision, the universe's future becomes one of gradual decay. Stars, the brilliant furnaces that illuminate the cosmos, will burn through their fuel and extinguish one by one. Planets will drift alone in an ever-expanding void, and black holes will continue to consume whatever matter remains. But even black holes, with their powerful gravitational pull, will eventually lose their energy over vast stretches of time, slowly evaporating into nothingness. The universe in this scenario will become a vast, dark, lifeless expanse, an eternal night. But how do we reconcile this future with the sheer beauty and complexity we witness in the universe today? The dazzling array of galaxies, each teeming with stars, planets, and perhaps life, seems in stark contrast to the bleak future of cosmic isolation. Our own Milky Way galaxy, which contains over 100 billion stars, is only one of countless galaxies spread across the vast reaches of space. When we look up at the night sky, we are witnessing a slice of the universe in all its vibrant, energetic glory. And yet, the future of this same universe seems to be one of inevitable decline. This stark contrast, between the universe as it is and the universe as it may one day be, strikes at the very heart of human curiosity. As we look out into the stars, we wonder how long this beauty will last. Will the universe continue to expand, growing colder and emptier until all that remains are the remnants of stars that once shone brightly? Or is there a way to alter its course, to avoid the inevitable fate of cosmic isolation? These questions haunt our understanding of the cosmos, and our search for answers has led us down countless paths of inquiry, from theoretical physics to existential philosophy. At the core of this search lies the mystery of dark energy. Scientists do not yet understand what dark energy is or how it works, but its effects on the universe are undeniable. It is this mysterious force that is driving the accelerated expansion of the cosmos, pushing galaxies farther apart at an ever-increasing rate. The discovery of dark energy has raised more questions than it has answered, but it has also opened new doors of possibility. Could it be that dark energy holds the key to understanding not only the universe's expansion but its eventual fate? The very nature of dark energy challenges our current understanding of physics. For decades, scientists believed that the expansion of the universe would slow down over time, eventually halting and reversing as gravity began to pull matter back together. But dark energy defies this expectation, forcing the universe to expand faster and faster. Some have even speculated that dark energy might be a product of the very fabric of space-time itself, a property of the universe that we have yet to fully comprehend. The accelerating expansion of the universe creates a paradox. On one hand, it is awe-inspiring to think that the cosmos is growing, expanding, and evolving. On the other hand, it raises a chilling prospect, an endless, cold, and desolate universe, where all energy dissipates into nothingness. This idea of a universe that continues to expand forever, growing increasingly inhospitable to life, is both awe-inducing and terrifying. But even as we grapple with these unsettling possibilities, the mystery of the universe's future remains tantalizingly unresolved. Is there a chance that the expansion will slow down or reverse? Could some unforeseen force intervene and alter the course of cosmic destiny? Or will the universe continue on its current trajectory, ultimately stretching out into a future where stars burn out and galaxies drift alone in a vast, empty expanse? As we ponder these questions, we are confronted with a fundamental truth. We are just beginning to understand the true nature of the universe. What we have learned so far is just the tip of the iceberg. The deeper we peer into the cosmos, the more we realize how much we don't know. And it is this uncertainty that makes the search for answers so compelling. The future of the universe, its ultimate fate, and our place within it are questions that continue to drive scientists and philosophers alike. The answers may be beyond our current understanding, but that doesn't stop us from asking. And in the asking, we move one step closer to uncovering the mysteries that lie ahead. Time is one of the most enigmatic aspects of our existence. It governs everything from the rise and fall of civilizations to the very motion of the stars and galaxies. Yet, despite its central role in shaping the universe, time itself remains an abstract concept that eludes precise understanding. For centuries, philosophers and scientists have pondered the nature of time, trying to unlock its mysteries. Is it a fundamental aspect of the universe, woven into the very fabric of reality? Or is it simply an illusion, a construct of human consciousness designed to make sense of the chaos around us? One of the most profound insights into the nature of time came from the groundbreaking work of Sir Isaac Newton. Newton's laws of motion and universal gravitation painted a picture of time as an absolute, unchanging force. According to Newtonian physics, time flows uniformly for everyone, everywhere, regardless of what happens in the world around them. It was an idea that gave rise to a sense of order and predictability in the universe, offering a comforting certainty about the flow of events. Time, in this view, was a linear, unstoppable force, an arrow that moved steadily forward from past to present to future. However, this seemingly straightforward understanding of time would soon be challenged by one of the most profound revolutions in science, Albert Einstein's theory of relativity. Einstein's insights radically altered our conception of time, revealing it to be a far more flexible and strange phenomenon than anyone had ever imagined. According to Einstein, time is not an absolute entity but is instead relative to the observer's motion and position in space. This revolutionary idea was encapsulated in his famous equation, E equals mc squared, which showed that energy and mass are interchangeable, and that time itself is intertwined with the fabric of space. In other words, time and space are not separate, independent realms, but two aspects of the same thing, spacetime. Einstein's theory showed that time could be stretched or compressed depending on how fast an object is moving or how strong the gravitational field is. This means that time flows differently for people who are traveling at different speeds or who are near massive objects like planets or black holes. The closer one gets to the speed of light, the slower time passes relative to someone standing still. Similarly, time moves more slowly near massive objects with strong gravitational fields. These mind-bending revelations challenged our traditional notions of time as a constant, fixed force. But perhaps the most profound and unsettling implication of Einstein's theory is that time as we experience it is not a fixed or universal phenomenon at all. In fact, time appears to be flexible, bendable, and even malleable. It is as though time itself is not a constant, but something that can be shaped and influenced by the forces at work in the universe. This idea raises an intriguing and disconcerting question. If time is not as fixed as we once thought, what does this mean for the future? If time itself is subject to the whims of space and gravity, could it be that the future is not set in stone? Could it be that time is not a one-way arrow, but something that can be manipulated, altered, or even reversed? The notion of time's malleability takes us into the realm of one of the most intriguing concepts in modern physics, the arrow of time. The arrow of time is the idea that time flows in one direction, forward, rather than backward. This seems like an obvious truth to us, as we experience the passage of time in a linear fashion. But the question of why time flows in this direction and not the other has puzzled scientists and philosophers alike for centuries. If the laws of physics are symmetrical, if they work the same way forwards and backwards in time, then why does time always seem to move forward? Why does a broken glass not spontaneously reassemble itself? Or why do we not witness the unaging of an old person? The answer to this question lies in a concept known as entropy. Entropy is a measure of disorder or randomness in a system, and it is governed by the second law of thermodynamics, which states that in any closed system, entropy always increases over time. In simpler terms, the universe is constantly becoming more disordered as time progresses. This increase in disorder gives time its arrow, its direction. As entropy increases, systems move from a state of order to a state of chaos, and this process is irreversible. The universe, from the smallest particle to the largest galaxy, is steadily marching toward greater and greater disorder, making the passage of time feel like a one-way journey from order to chaos. But while the concept of entropy helps explain why time moves in one direction, it also suggests a grim reality. The universe as we know it is inevitably heading toward a state of maximum entropy, what is called heat death. Heat death is the point at which the universe reaches a state of thermodynamic equilibrium, where all matter and energy are evenly distributed, and no usable energy remains to do work. At this stage, stars will burn out, galaxies will drift apart, and the universe will become a dark, cold, lifeless expanse. In this scenario, the arrow of time reaches its ultimate destination, and the concept of a future as we understand it ceases to have meaning. The idea of heat death is both fascinating and terrifying. It suggests that the universe is not eternal, but rather has a limited lifespan, one that is defined by the relentless march of entropy. And yet, despite the bleakness of this vision, it raises an important question. Is this the only possible future for the universe, or is there a way to alter its course? If time is not an absolute force but something that is shaped by the fabric of space, then could it be possible to manipulate time itself, to slow it down, speed it up, or even reverse its flow? As we stand on the precipice of understanding time's true nature, we are forced to confront some deeply unsettling possibilities. The arrow of time may be irreversible, but the future is not set in stone. While the second law of thermodynamics suggests that the universe will eventually reach a state of maximum entropy, there may be other forces at play, forces that we have yet to fully comprehend. Could there be mechanisms at work in the universe that could slow or reverse the effects of entropy? Could there be ways to manipulate time, bending it to our will, as some of the most speculative theories in physics suggest? These questions invite us to imagine a future where time itself becomes a malleable force, one that could be shaped and controlled by advanced technology or deeper understanding of the laws of nature. Could humanity one day learn to master time, to escape its inevitable march toward the future? Or are we doomed to be forever trapped in the unyielding flow of time, swept along by forces that are far beyond our control? In the end, time remains one of the greatest mysteries of the universe. It governs everything, yet we know so little about its true nature. The more we learn, the more questions arise. Is time simply a linear progression from past to future, Or is it something more complex, something that could be bent, shaped, or even defied? As our understanding of space, gravity, and the fundamental laws of physics continues to evolve, so too will our understanding of time itself. And perhaps, in the not-too-distant future, we will unlock the secrets of time. Secrets that could change everything, including our place in the vast, mysterious cosmos. In the vast cosmos, there exists a force so powerful that it influences the very fabric of space and time, yet remains invisible and elusive to our understanding. This force, known as dark energy, has puzzled scientists for decades, and remains one of the most profound mysteries in modern physics. But what exactly is dark energy and how does it shape the future of the universe? The story of dark energy began in the late 20th century, when astronomers made a startling discovery that would challenge everything we thought we knew about the universe. For most of human history, it was believed that the expansion of the universe was slowing down. After all, the gravitational pull between galaxies should eventually bring them together, halting the expansion and causing the universe to collapse in on itself. This idea, known as the Big Crunch, seemed like the inevitable fate of all cosmic matter. However, in the late 1990s, two independent teams of astronomers made a discovery that defied this expectation. They were studying distant supernovae, exploding stars that shine with incredible brightness, and what they found was nothing short of astounding. Instead of the universe's expansion slowing down, as they had expected, it was actually accelerating. Galaxies were moving farther apart from each other at an increasingly faster rate. This unexpected acceleration sent shockwaves through the scientific community, as it suggested that some unseen force was at work, driving the universe apart. This force, which was responsible for the accelerating expansion, was later dubbed dark energy. But despite its profound influence on the universe's evolution, dark energy remains one of the most enigmatic phenomena in modern physics. Unlike gravity or electromagnetism, which are well-understood forces, dark energy is invisible, undetectable, and fundamentally different from anything we've encountered before. It does not interact with light, matter, or radiation in any measurable way. It is neither matter nor energy in the traditional sense. In fact, its very existence raises more questions than answers. Dark energy is thought to make up about 70% of the total energy content of the universe. This staggering proportion means that it has a profound effect on the structure and fate of the cosmos. Yet, for all its influence, dark energy remains a complete mystery. We have no idea what it is made of, how it behaves, or why it even exists. What we do know is that its presence is essential to the current state of the universe. Without dark energy, the expansion of the universe would be slowing down, eventually halting and reversing. Instead, the universe is expanding at an accelerating rate, pushing galaxies further apart with each passing moment. To understand the role of dark energy, it's helpful to first consider the role of gravity. Gravity is the force that pulls matter together, causing stars to form, planets to orbit, and galaxies to cluster. It is a force of attraction, one that counteracts the effects of expansion. But dark energy behaves in exactly the opposite way. Rather than pulling things together, it pushes them apart. Dark energy exerts a repulsive force, driving galaxies away from one another at an ever-increasing rate. The implications of dark energy's influence are profound. As the universe continues to expand, the effects of dark energy will become more pronounced. In the far future, as galaxies drift further apart, the universe will become increasingly isolated. Stars will burn out, galaxies will be separated by unimaginable distances, and the cosmos will grow colder and darker. This scenario, known as the Big Freeze, predicts a universe where all the energy is spread so thin that life as we know it becomes impossible. The universe will become a vast, empty expanse, with no stars to light the way and no galaxies to explore. But what if dark energy is not just a passive force but an active one? What if it is something that evolves over time, changing the fate of the universe in ways we can't yet predict? Some scientists have speculated that dark energy might not be a constant force but could fluctuate in strength, causing the expansion of the universe to accelerate or decelerate at different rates. Could dark energy be the key to understanding the true future of the cosmos? If we could understand its properties, might we be able to predict whether the universe will continue to expand forever, or if something else will occur? One of the most intriguing questions surrounding dark energy is whether it could one day reverse the expansion of the universe. While the current evidence points to an ever-accelerating expansion, it is not entirely clear whether this acceleration will continue indefinitely. Could there be a point at which the rate of expansion slows down and eventually reverses, leading to the Big Crunch? Or could dark energy be the key to a completely different fate for the universe, one that we have yet to fully comprehend? As scientists continue to study dark energy, they are faced with a number of challenges. The most fundamental of these challenges is the fact that dark energy cannot be directly observed. It does not emit light, heat, or any other form of detectable radiation. It cannot be measured in the same way that we measure other forces in the universe. Instead, its existence is inferred from its effects on the cosmos, particularly the accelerated expansion of the universe. This indirect evidence raises the question: how much of what we know about dark energy is simply an approximation, a best guess based on our current understanding of physics? Could there be aspects of dark energy that we are completely missing, hidden beyond the reach of our current observational tools? One of the most significant challenges in studying dark energy is that it behaves in ways that contradict our intuition. We are accustomed to thinking of energy as something that can be harnessed and used, something that can be converted into power or motion. But dark energy does not work in this way. It does not provide any usable energy for life or for any practical purpose. Instead, it appears to be an abstract force that shapes the universe in ways we can't yet fully understand. This has led some scientists to wonder if dark energy is simply a consequence of the structure of space itself, a property of the cosmos that we are only beginning to grasp. The very existence of dark energy challenges our current models of the universe. For centuries, physicists have relied on the laws of gravity, electromagnetism, and quantum mechanics to explain the behavior of matter and energy. But dark energy seems to operate outside of these laws, suggesting that there may be fundamental forces or principles of the universe that we have yet to discover. Could dark energy be a clue to a deeper, more unified theory of the cosmos, one that combines the forces of gravity, electromagnetism, and quantum mechanics into a single, coherent framework? As we continue to probe the mysteries of dark energy, we are confronted with a fundamental question. What does dark energy mean for the future of the universe? If dark energy continues to drive the expansion of the cosmos, the universe will continue to grow colder, darker, and emptier over time. Galaxies will drift further apart, stars will burn out, and the universe will eventually reach a state of maximum entropy, where no energy remains to do any work. This is the grim vision of the universe's future that dark energy suggests. But could there be other possibilities? Could dark energy somehow be harnessed, understood, or even manipulated by future generations of scientists? Or is dark energy simply a force that will determine the fate of the cosmos, regardless of our understanding? The mystery of dark energy is far from solved. As we look to the future, we are left with more questions than answers. What is dark energy? Where did it come from? And how will it shape the ultimate fate of everything in the universe? These are questions that may take centuries or even millennia to answer. But one thing is certain: dark energy is one of the most significant and mysterious forces in the universe, and its role in the future of the cosmos is something that will continue to captivate and perplex scientists for generations to come. Black holes are among the most mysterious and awe-inspiring phenomena in the universe, objects so strange that they seem to defy the laws of physics. These cosmic giants have captivated the imagination of both scientists and the public alike, inspiring a vast body of research, speculation, and even science fiction. But despite their prominence in popular culture, black holes remain one of the greatest puzzles in modern astrophysics, with their true nature and role in the universe still shrouded in mystery. The story of black holes begins with the work of Albert Einstein. His theory of general relativity, published in 1915, revolutionized our understanding of gravity and spacetime. According to general relativity, massive objects like stars and planets bend the fabric of spacetime, creating what we perceive as gravity. This bending of spacetime is not just a force pulling objects towards each other, it's a warping of the very structure of the universe. When a massive star collapses, it warps spacetime so severely that it creates a singularity, a point of infinite density where the laws of physics as we know them break down. This is the essence of a black hole. The concept of a black hole was first proposed by the British mathematician John Michell in the 18th century, but it wasn't until the 20th century, with the advent of Einstein's theories, that the idea gained scientific credibility. In the 1960s, the work of physicist John Wheeler brought the term black hole into popular use. But it was the discovery of the first black hole, Cygnus X-1, in the 1970s that confirmed their existence beyond theory. Since then, black holes have become central to our understanding of the cosmos, challenging our very notions of space, time, and reality itself. At the core of a black hole lies the singularity, a point of infinite density where the gravitational forces are so intense that not even light can escape. This is the heart of the black hole, where all the mass of the object is concentrated. The gravitational pull near a singularity is so strong that it distorts the very fabric of space-time, creating a region from which nothing, neither matter nor radiation, can escape. This boundary is called the event horizon, and it marks the point of no return. Once something crosses the event horizon, it is trapped forever, unable to escape the relentless pull of gravity. The idea of a singularity is both mind-boggling and terrifying. It represents a breakdown of our understanding of the laws of physics. In classical mechanics, we are taught that mass and energy are conserved, that nothing can be infinitely dense or infinitely small. But black holes seem to violate these rules, existing in a state that defies our understanding of the universe. What happens at the singularity? What lies beyond it? These questions remain unanswered, tantalizing scientists with the possibility that there may be laws of nature yet to be discovered, hidden deep within the heart of black holes. One of the most perplexing aspects of black holes is their role in the larger structure of the universe. These objects are not just isolated anomalies, they are fundamental to the workings of galaxies themselves. It is now widely believed that every large galaxy, including our own Milky Way, contains a supermassive black hole at its center. These supermassive black holes can have masses millions or even billions of times that of our Sun. They are thought to play a key role in the formation and evolution of galaxies, shaping their structure and influencing the dynamics of stars and planetary systems. The presence of a supermassive black hole at the center of a galaxy is not a coincidence. The gravitational pull of these black holes affects the motion of stars, gas, and dust in the galaxy, regulating the flow of matter and energy. In some cases, black holes may even drive the formation of new stars by compressing gas to extreme densities. But they also have a destructive side. As black holes grow, they can consume vast amounts of matter, including entire stars. This process, known as accretion, generates enormous amounts of radiation, often in the form of powerful X-rays. These intense bursts of energy can influence the surrounding environment, heating up gas and dust, and even driving the expulsion of matter from the galaxy in the form of powerful jets. The energy emitted by black holes is so intense that it can be seen across vast distances, making them some of the brightest objects in the universe. In fact, the discovery of quasars, ultra-bright, distant objects powered by supermassive black holes, was one of the key breakthroughs in modern astronomy. Quasars are among the most energetic and distant objects known, emitting more energy than entire galaxies. Their discovery has provided us with valuable insights into the early universe, as many quasars are found at the edges of the observable cosmos, where they formed billions of years ago. Despite their immense power, black holes also present a paradox. They are both the most destructive and the most mysterious objects in the universe. On one hand, they have the ability to devour entire stars and galaxies, tearing apart anything that ventures too close. On the other hand, they may hold the key to some of the most profound mysteries of the universe, including the nature of space, time, and gravity. The study of black holes offers a unique window into the deepest workings of the cosmos, allowing scientists to probe the very edges of our understanding. One of the most intriguing questions surrounding black holes is what happens to information that falls into them. According to the laws of quantum mechanics, information cannot be destroyed. Yet, once something crosses the event horizon of a black hole, it seems to disappear forever. This paradox, known as the black hole information paradox, has been the subject of intense debate among physicists. Some theorists believe that information may not be lost after all, but is instead encoded in subtle quantum processes at the event horizon. Others suggest that black holes may be able to leak information in some form, such as through the radiation they emit, a phenomenon known as Hawking radiation, named after the famous physicist Stephen Hawking. Hawking's groundbreaking work in the 1970s showed that black holes are not completely black. Instead, they emit a faint radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, is thought to be responsible for the gradual evaporation of black holes over time. As black holes lose mass through this radiation, they will eventually shrink and vanish entirely. This process, while taking billions of years for large black holes, raises another fundamental question. What happens to the information contained within a black hole as it evaporates? Does it vanish forever, or is it somehow preserved in the quantum field surrounding the black hole? This remains one of the most profound unanswered questions in modern physics. The ultimate fate of black holes is still uncertain. Will they continue to grow, consuming matter and energy until they dominate the entire universe? Or will they eventually evaporate, leaving behind only faint remnants of their once mighty existence? Some theories suggest that black holes could eventually merge into even larger black holes, creating a network of interconnected singularities that could reshape the structure of the cosmos. Others propose that black holes might play a role in the birth of new universes, serving as gateways to alternate dimensions or as the seeds of cosmic rebirth. Whatever their fate, black holes are an essential part of the universe's grand narrative. They are not just distant objects, isolated from the rest of the cosmos. They are the crucibles in which the deepest mysteries of space and time are forged. As we continue to probe the secrets of black holes, we may find answers to some of the most profound questions about the universe and our place within it. But for now, black holes remain as enigmatic as ever, both the destroyers of stars and the keepers of the universe's most tantalizing secrets. In the grand scale of the universe, there exists a phenomenon that, despite its importance, has largely remained invisible to the human eye for most of history. Yet, without it, the cosmos as we know it could not exist. This elusive force is gravity, a fundamental force that governs everything from the orbits of planets around stars to the paths of galaxies through the cosmos. It is both simple and profound, a force that shapes the structure of the universe yet remains largely mysterious in its full scope. At its most basic level, gravity is the force that pulls objects toward each other. It is what keeps us anchored to the Earth, what causes an apple to fall from a tree, and what ensures that the moon orbits our planet. But gravity is far more than just the force that governs everyday objects. It is the force that holds galaxies together, that binds stars and planets, and that shapes the very structure of spacetime itself. The concept of gravity is as old as human civilization itself. Ancient cultures, from the Greeks to the Chinese, had various understandings of gravity, though none could explain it in the way we understand it today. It was Sir Isaac Newton, in the late 17th century, who first formulated a universal law of gravitation. Newton's law of gravitation proposed that every object in the universe exerts a force on every other object, and that this force is proportional to the masses of the objects and inversely proportional to the square of the distance between them. This simple yet revolutionary insight explained not only the motion of objects on Earth, but also the movements of the planets in our solar system. Newton's laws of motion and gravity gave rise to a universe that was predictable and deterministic. If you knew the mass of an object and the distance between two objects, you could calculate their gravitational attraction. This understanding of gravity allowed humanity to make incredible advances in science, from launching satellites into space to understanding the dynamics of celestial bodies. However, Newton's laws, while groundbreaking, were not the final word on gravity. As scientists probed deeper into the mysteries of the universe, they found that gravity was even more profound and complex than they had imagined. The next great leap in understanding gravity came in the early 20th century, with the publication of Albert Einstein's theory of general relativity. Einstein's theory revolutionized our understanding of gravity by showing that it is not simply a force that pulls objects toward each other, as Newton had described. Instead, gravity is a result of the warping of spacetime itself. According to general relativity, massive objects like stars and planets bend the fabric of space and time around them, creating what we perceive as gravity. The larger the object, the more it distorts spacetime, and the stronger the gravitational pull. This was a profound shift in understanding. Gravity was no longer seen as an invisible force acting at a distance but as a warping of the very fabric of the universe. Einstein's theory of general relativity also predicted the existence of black holes, regions of space where gravity is so strong that not even light can escape. This prediction was initially met with skepticism, but in the decades that followed, evidence began to mount that black holes were not just theoretical curiosities, but real objects that existed in the universe. The discovery of black holes and their relationship to gravity has had profound implications for our understanding of spacetime. In fact, black holes may be the key to unlocking some of the greatest mysteries of the universe, including the nature of time itself. The study of gravity has also led to one of the most intriguing questions in modern physics: the nature of dark matter. For decades, astronomers have observed the motion of galaxies and clusters of galaxies, and they have noticed that the gravitational pull in these systems is far stronger than what can be explained by the visible matter that we can observe. This has led scientists to propose the existence of dark matter, a form of matter that does not emit light or radiation, but that exerts a gravitational pull on visible matter. Dark matter is thought to make up about 27% of the universe's mass, yet it remains completely invisible, detectable only through its gravitational effects. While dark matter is still a mystery, its gravitational influence is undeniable. It is thought to play a key role in the formation of galaxies, helping to hold them together. Without dark matter, galaxies would not have the gravitational pull necessary to prevent their stars from flying off into space. Dark matter's role in the structure of the universe underscores the importance of gravity as a shaping force. Gravity, it seems, is not only responsible for holding stars and planets together, but also for governing the very distribution of matter in the universe itself. But perhaps one of the most profound revelations in the study of gravity is the concept of gravitational waves. First predicted by Einstein in 1916, gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves travel at the speed of light, carrying information about the events that cause them. For nearly a century, gravitational waves remained theoretical, but in 2015, scientists detected them for the first time, confirming one of Einstein's most profound predictions. The detection of gravitational waves opened up a new era in astrophysics, providing a new way of observing the universe. Gravitational waves offer a glimpse into the most violent and extreme events in the universe. When two black holes collide, they send ripples through spacetime, which can be detected by instruments on Earth. These waves carry information about the properties of the objects involved in the collision, allowing scientists to study objects that are otherwise invisible, such as black holes and neutron stars. In this way, gravity has become a tool for observing the universe in ways that were once unimaginable. Despite all that we have learned about gravity, there is still much that remains unknown. Gravity is, by far, the weakest of the fundamental forces, yet it governs the behavior of large-scale structures in the universe. It can be attractive and repulsive depending on the context, and it shapes the very structure of spacetime itself. But we still don't fully understand how gravity works on the quantum scale. For example, the force of gravity at the level of individual particles does not seem to behave in the same way as the other fundamental forces, such as electromagnetism or the strong nuclear force. This has led to one of the greatest unsolved problems in physics: the search for a theory of quantum gravity that can reconcile general relativity with quantum mechanics. The nature of gravity also raises questions about the very fabric of the universe. If gravity can bend spacetime, what does this mean for the nature of time itself? Could gravity, and the warping of spacetime, be the key to understanding the true nature of time, whether it is something absolute and unchanging or something flexible and dynamic? The relationship between gravity, space, and time is one of the most profound questions in modern physics, and it is a question that continues to shape our exploration of the universe. As we continue to probe the depths of space, we are also confronted with the most basic question of all: how does gravity shape the future of the universe? Will the force that binds galaxies together eventually tear them apart? Will gravity continue to shape the evolution of the cosmos, guiding the birth and death of stars, and determining the fate of galaxies? Or will the nature of gravity itself change as we discover more about the universe, leading to new insights into its ultimate destiny? Gravity is a force that shapes the universe on the grandest scale, and yet, it remains one of the most elusive and mysterious forces in nature. From the formation of galaxies to the collision of black holes, gravity is the invisible hand that guides the evolution of the cosmos. As we continue to explore the universe, we will undoubtedly uncover more secrets about gravity, its role in the structure of spacetime, and its ultimate influence on the fate of everything that exists. It is a force that will continue to captivate our imagination, challenge our understanding, and reveal the deepest truths of the universe. In the search for the ultimate fate of the universe, one concept stands out as both a foundational and deeply troubling idea: entropy. Entropy, at its core, is a measure of disorder or randomness in a system, and it is one of the most fundamental principles in physics. According to the second law of thermodynamics, entropy always increases over time in any closed system. This law suggests that over time the universe itself is steadily moving toward a state of maximum disorder, where all matter and energy are evenly distributed and no usable energy remains to perform work. This scenario, known as the heat death of the universe, presents a vision of the future that is both awe-inspiring and terrifying. It is a future where, despite all the beauty, complexity, and life that currently exist, everything will eventually succumb to a slow, inevitable decline into an empty, lifeless void. The concept of entropy is essential to understanding the ultimate fate of the cosmos. In essence, entropy is the measure of how much energy in a system is unavailable to do useful work. In simpler terms, it's the tendency of systems to move from a state of order to one of disorder. A simple example of this is the melting of ice. When ice melts, the orderly structure of its molecules breaks down, and the system becomes more disordered. In the universe, this trend toward disorder is all-encompassing. Stars burn through their fuel and eventually die, galaxies collide and merge, and even the most stable forms of matter eventually decay over vast stretches of time. In every corner of the universe, entropy is at work, steadily eroding the structures that we find so beautiful and so intricate. In practical terms, the second law of thermodynamics means that the universe is always running out of usable energy. As energy becomes more evenly distributed, the ability to do work diminishes, and systems become increasingly disordered. Eventually, in a universe where entropy has reached its maximum, there will be no gradients of energy, no differences in temperature, pressure, or other forms of energy. All matter will have spread out so evenly that there will be no more processes that can generate work. Stars will no longer burn, and galaxies will drift apart in a dark, cold expanse, each particle isolated from the others. This state, known as the heat death, represents the ultimate end point for the universe, where no more thermodynamic processes can take place, and life as we know it becomes impossible. The concept of heat death raises unsettling questions about the very nature of time itself. If the universe is destined to run down into a state of maximum entropy, what does this mean for the passage of time? Time, as we experience it, is linked intimately to the flow of energy and the processes of life. Our very perception of time is tied to the changes we observe around us. The ticking of a clock, the aging of our bodies, the birth and death of stars. As entropy increases and the universe winds down, the flow of time could slow to a crawl. The familiar rhythms of life, the motion of the planets, and the cycles of the seasons might seem less relevant in a universe where nothing happens anymore, where all systems are in equilibrium and no energy is available to drive change. But it's not just the future of the universe that is shaped by entropy. Entropy also plays a role in the present, influencing everything from the behavior of particles to the dynamics of galaxies. One of the key ways that entropy manifests in our daily lives is through the process of energy transfer. When energy moves from one system to another, it always tends to move in a way that increases the overall entropy of the universe. For example, when we use energy to power a car or run a computer, some of that energy is inevitably lost to heat. This heat dissipates into the surroundings, increasing the disorder in the system. In fact, the efficiency of any process is limited by the second law of thermodynamics. No machine, no matter how advanced, can operate at 100% efficiency because some energy is always lost to entropy. This principle of energy conservation and the tendency of systems to move toward greater disorder can also be seen on the scale of the cosmos. Stars, for example, are vast engines that burn hydrogen to create light and heat. However, as stars age and burn through their fuel, they begin to lose their ability to produce energy in a stable and controlled manner. This process is known as stellar evolution, and it ultimately leads to the death of the star. Depending on its mass, a star may become a white dwarf, a neutron star, or a black hole. In any case, the star's once orderly fusion process eventually gives way to an increasing level of chaos, as the star loses energy and breaks down into more disordered states. Similarly, galaxies themselves undergo a similar transformation. Over billions of years, galaxies collide, merge, and reorganize, creating complex structures and phenomena, but eventually the energy within those galaxies will be spread out too thinly to sustain any meaningful activity. One of the most fascinating aspects of entropy is its relationship to the concept of time. The increase in entropy is often thought of as what gives time its direction. This is known as the arrow of time, the idea that time moves forward in a specific direction from the past to the future. The second law of thermodynamics provides a clear explanation for why this is the case. The increase in entropy marks a direction in time because as systems become more disordered, they naturally move from a state of low entropy, more order, to high entropy, less order. This progression gives time its forward-moving arrow, as processes that increase entropy are irreversible. You can't unscramble an egg and you can't put the energy lost to heat back into a system. In this way, entropy helps to define the passage of time, setting the stage for the unfolding story of the universe. The inexorable rise of entropy is not merely a scientific concept. It is a powerful metaphor for the inevitable decline of all things. In a way, entropy reflects the human condition itself. Our lives, like the universe, are subject to forces that move us from a state of order to one of disorder. Our bodies age, our societies change, and civilizations rise and fall. The second law of thermodynamics provides a universal context for this decay, offering a scientific parallel to our existential awareness of impermanence. We are constantly surrounded by entropy, from the aging of our bodies to the eventual heat death of the universe. The steady march of entropy forces us to confront the nature of time, existence, and our place within the grand story of the cosmos. Despite the seemingly bleak implications of entropy, There is a sense of wonder in the realization that the universe has been shaped by this very force. The complexity and beauty of the cosmos, from the intricate dance of particles to the formation of stars and galaxies, are all manifestations of the flow of energy through the universe, driven by entropy. The fact that the universe has been able to sustain life for billions of years, against the backdrop of an ever-increasing entropy, is a testament to the remarkable resilience and creativity of nature. Life itself, in a sense, is a rebellion against entropy. Living systems are able to create pockets of order amidst the chaos, to harness energy and create complex structures that temporarily stave off the relentless march of disorder. But ultimately, no system can escape the effects of entropy forever. As we look toward the distant future, the increasing dominance of entropy in the universe presents a sobering thought. The universe, as it expands and cools, will eventually reach a point where no energy remains to do meaningful work. Stars will burn out, galaxies will drift apart, and the universe will become a vast, cold, dark expanse, a state of perfect equilibrium. The heat death of the universe, while still billions of years away, will mark the final end of all processes, an eternal stasis where time and space are no longer meaningful concepts. But despite the inevitability of entropy, there is something profoundly beautiful about the way the universe has unfolded. The story of the cosmos, from its violent birth in the Big Bang to the complexity of life on Earth, is a testament to the incredible forces that have shaped it. Entropy may be the ultimate fate of the universe, but in its wake, it leaves behind a legacy of awe-inspiring beauty and wonder. As we stand on the edge of the cosmic story, we are reminded that, in the face of entropy's inexorable rise, the universe has still created something remarkable: life, consciousness, and the potential to understand the very forces that govern its existence. As we delve deeper into the fabric of the cosmos, one of the most mind-bending and awe-inspiring aspects of the universe comes into view: the concept of time. Time is a fundamental part of human existence, and yet it remains one of the most mysterious and perplexing aspects of reality. We measure it, we live by it, and we experience it, but what exactly is time? How does it function within the vast expanse of the universe, and what does it mean for the future of everything? At a glance, time seems like an incredibly simple concept. It's a straight line, marked by the ticking of a clock and the turning of the calendar. Time moves forward, one moment after the next, from past to present to future. We live in time, and time lives within us. We age, we experience events, we plan for the future. It's a constant, unyielding force that defines our lives in ways both big and small. But if we step back and look at the cosmos through the lens of physics, time becomes anything but simple. Time is deeply intertwined with space in a way that defies our usual understanding of both. The theory of relativity, proposed by Albert Einstein in the early 20th century, revolutionized our perception of time by showing that it is not an absolute, universal constant. In fact, time is relative. It bends, warps, and stretches depending on factors like gravity and velocity. Time, in this view, is no longer just a steady march forward but a flexible dimension, shaped by the forces of the universe. Einstein's general theory of relativity describes how the fabric of space and time, collectively known as spacetime, is curved by massive objects. The more massive an object, the more it distorts spacetime, and the more it warps the passage of time itself. This means that time moves more slowly in stronger gravitational fields. A clock near a black hole, for instance, ticks far slower than a clock on Earth, due to the immense warping of spacetime in such regions. This is known as time dilation, and it is a fundamental feature of the universe that has been confirmed through numerous experiments. The closer we get to massive objects, the more time stretches, and the further we move away, the faster time seems to move. This bending of time has extraordinary implications. The most striking one is the idea of time travel. If time can be bent and manipulated by gravity and velocity, could we, in theory, travel through time? In a way, we already do. We travel through time every second of our lives, moving forward into the future. But could we go back in time or travel to the distant future in an instant? Some physicists believe it's possible, at least in theory. They suggest that if we could somehow travel faster than the speed of light, we might be able to break through the fabric of spacetime and access different points in time. This, however, remains purely speculative, as the laws of physics as we know them prohibit anything from exceeding the speed of light. Even more intriguing is the possibility that time might not be as linear as we experience it. What if time is not a straight line at all but a more complex structure? According to some theories, time might exist in multiple dimensions, allowing for the possibility of time loops, parallel timelines, or even an infinite number of alternate realities. In such a model, time is not something we move through, but something we are part of, a vast, multidimensional landscape where the past, present, and future might be much more interconnected than we currently understand. This vision of time challenges everything we think we know about reality, suggesting that time might be far more malleable and multifaceted than we could ever imagine. Another mind-bending concept related to time is the idea of the arrow of time. The arrow of time refers to the one-way direction in which time seems to move, from past to present to future. This concept is intricately linked to entropy, the measure of disorder in a system. The second law of thermodynamics tells us that the entropy of an isolated system always increases, meaning that systems tend to move toward more disordered states over time. This increase in entropy gives time its direction. The reason we don't see events moving backward, eggs don't spontaneously unscramble, broken glasses don't reassemble themselves, is due to the natural progression toward higher entropy. Time moves forward because disorder increases with time, and the universe is constantly moving toward greater disarray. However, there are paradoxes within this framework that challenge our understanding of time. One of the most famous of these paradoxes is the grandfather paradox, which asks what would happen if you were able to travel back in time and alter events in such a way that your grandfather never met your grandmother. If your grandfather never existed, you would never have been born, and therefore you would never have traveled back in time in the first place. This paradox raises the question of whether time travel is possible at all. If the timeline is fixed and unchangeable, as the grandfather paradox suggests, then it would be impossible to alter events in the past. But if the timeline is mutable and events in the past can be changed, it opens up a host of new possibilities, and a host of new problems. For now, time remains one of the greatest mysteries of the universe. It governs everything we know, yet we still don't fully understand its nature. Despite our ability to measure time with incredible precision, we lack a complete theory that explains what time truly is, why it moves in the direction it does, and whether it is an illusion or a fundamental aspect of the universe. Is time an intrinsic feature of reality, or is it simply a human construct, a convenient way of organizing our experiences? Is the flow of time a constant, or does it change depending on our perspective or the conditions around us? The nature of time also raises questions about the fate of the universe. If time is tied to the expansion of the cosmos, then what happens when the universe reaches a state of maximum entropy, when all matter and energy are evenly distributed and no more work can be done? Will time itself come to an end, as the universe enters a state of eternal stasis? Or will time continue to exist in some form, even as the cosmos winds down? These questions are central to understanding the long-term future of the universe and the role that time plays in its ultimate fate. The concept of time is also deeply intertwined with the concept of death, both the death of individual beings and the eventual death of the universe itself. The passage of time brings with it decay, aging, and the inevitable end of all living things. Every moment we experience is a moment closer to our own mortality, and yet, it is through our awareness of time that we are able to live fully, to make choices, and to experience the richness of life. Time is a paradox. While it is the force that carries us toward the end, it is also the force that allows us to appreciate the beauty of existence, to forge relationships, to create art, and to pursue knowledge. As we look to the future, we are left with the profound mystery of time. What does time truly mean in the context of the universe? Is it simply a measurement, a tool for organizing events, or is it a deeper, more fundamental feature of reality? Can we ever truly understand time, or is it destined to remain an enigma, as much a part of the human experience as it is a part of the cosmos? Time, like the universe itself, continues to unfold, and in its wake, it leaves us with more questions than answers. Whether we can unlock the true nature of time or not, it will continue to shape the story of everything, from the birth of stars to the evolution of life, to the distant future of the cosmos. And as we stand at the crossroads of our understanding, we are reminded that time is not just the ticking of a clock, but the thread that connects us to the universe, to each other, and to the mysteries that await. The idea of a multiverse, multiple parallel universes existing alongside our own, has captured the imagination of scientists, philosophers, and storytellers alike for decades. While the concept sounds like something out of science fiction, it has gained increasing attention in modern cosmology and theoretical physics. The idea that our universe may not be the only one, but rather part of a vast and complex network of universes, opens up fascinating possibilities about the nature of reality, existence, and the future of everything. But what does the multiverse really mean? Is there any evidence to support it, or is it simply a theoretical abstraction that may never be proven? The multiverse hypothesis has its roots in several areas of theoretical physics, but one of the most significant foundations comes from the field of cosmology. The Big Bang Theory, which describes the origin of our universe, has been the dominant model for understanding the creation and evolution of the cosmos. According to the Big Bang model, the universe began as an infinitely small and hot point, known as a singularity, and then expanded rapidly in a process called cosmic inflation. This rapid expansion caused the universe to cool and form the structures we see today, such as galaxies, stars, and planets. However, cosmic inflation raises an intriguing possibility. If our universe expanded from a singular point, then there could be other regions of space that also underwent inflation, leading to the formation of other bubble universes. This idea is known as the inflationary multiverse. The inflationary multiverse suggests that our universe is just one of countless bubbles that have formed within a much larger, inflating space. Each bubble could have its own unique set of physical laws, constants, and properties, making each universe distinct from the others. In this framework, our universe is not unique but rather a small part of a vast and ever-expanding multiverse. The concept of a bubble universe is akin to the idea of soap bubbles, each with its own unique shape, size, and characteristics, but all existing within the same larger space. One of the most fascinating aspects of the multiverse theory is the possibility that different universes could have different physical laws. In our universe, we have come to understand certain constants that govern the behavior of matter, energy, and the fundamental forces such as the speed of light and the gravitational constant. These laws and constants are what allow the universe to exist in its current form. But in other universes, the laws could be completely different. The strength of gravity could vary, the mass of fundamental particles could be different, or the very nature of time and space could change. In some universes, the conditions might be so radically different that life as we know it could not exist. In others, the constants might align in such a way that life forms with entirely different properties could emerge. The idea of a multiverse also raises profound philosophical questions. If there are multiple universes, each with its own set of physical laws, does that mean that anything that is physically possible has already happened in some universe? Could there be universes where different versions of ourselves exist, where we made different choices, or where entire timelines diverged from the one we know? In this framework, the multiverse becomes a vast, ever-expanding network of possibilities, each universe representing a different outcome, a different reality. This idea touches on concepts of determinism, free will, and the nature of reality itself. If all possibilities are realized in different universes, does that mean that every choice, every potential outcome already exists somewhere in the multiverse? Or is it the very nature of the multiverse to give rise to infinite, unpredictable possibilities? There are also deeper implications for the concept of the multiverse when it comes to the fine-tuning of our universe. The observable universe appears to be perfectly tuned for the existence of life, with the constants and laws of physics seemingly arranged in a way that allows for the formation of stars, planets, and life itself. If the constants were even slightly different, life as we know it would be impossible. The fact that the universe is so finely tuned for life has long been a subject of debate, with some scientists arguing that the laws of physics simply happen to be what they are, while others suggest that this fine-tuning points to a deeper explanation. The multiverse hypothesis offers a possible solution to this puzzle. Perhaps we live in one of the universes where the conditions just happen to be right for life. In the vast expanse of the multiverse, it's statistically likely that some universes would have the right conditions for life to emerge, while others would not. The concept of a multiverse also connects to the idea of the anthropic principle, which suggests that the universe must have the properties it does because if it didn't, we wouldn't be here to observe it. In a sense, our universe appears fine-tuned for life because life is here to observe it. If there were a multiverse, however, the anthropic principle could take on a new significance. The existence of countless universes with varying properties might help explain why our universe is so perfectly suited for life. It is not because there is some grand design, but because in a vast multiverse, some universes were bound to have the right conditions for life to emerge. This idea reframes our understanding of the universe. Rather than being a singular, special creation, the universe is one of many, with life emerging simply because we happen to exist in the universe where the conditions for life are just right. Another intriguing aspect of the multiverse theory is the possibility that it could provide answers to some of the deepest questions in physics. For example, the multiverse hypothesis might help resolve the mysteries surrounding quantum mechanics and the measurement problem. In quantum mechanics, particles exist in a state of probability, existing in multiple states simultaneously until observed. This has led to the question, what happens when we observe a quantum system? One possible explanation is that each possible outcome of a quantum event occurs in a separate universe, creating a branching of timelines, each representing a different possibility. This idea, known as the many worlds interpretation of quantum mechanics, suggests that every time a quantum event occurs, the universe splits, with each branch representing a different outcome. If this idea is correct, it would mean that the multiverse is not just a theoretical abstraction but a real, physical phenomenon, with countless universes arising from every quantum event. Despite its elegance and intrigue, the multiverse theory faces significant challenges, particularly when it comes to evidence. Currently, there is no direct observational evidence that other universes exist. The multiverse is a hypothesis based largely on theoretical models, many of which are still in development. One of the biggest hurdles is the lack of a way to test for the existence of other universes. If other universes exist beyond our own, they may be completely disconnected from our own universe, making it impossible to observe or measure them. Some scientists argue that the multiverse is inherently untestable and therefore outside the realm of scientific inquiry. Others believe that indirect evidence, such as patterns in the cosmic microwave background radiation, could provide clues to the existence of a multiverse, but these ideas remain speculative. As we contemplate the implications of the multiverse theory, it becomes clear that it challenges some of our most fundamental assumptions about reality. If the multiverse is real, then the nature of existence is far more complex and diverse than we could have ever imagined. It forces us to rethink everything from the nature of life and consciousness to the fundamental structure of reality itself. The multiverse is a concept that stretches the boundaries of human imagination, offering a vision of the cosmos that is vast, interconnected, and full of infinite possibilities. Whether or not we will ever be able to prove the existence of other universes remains to be seen, but the multiverse hypothesis continues to be one of the most fascinating and profound ideas in modern cosmology. The end of the universe is a concept that stirs up profound questions about the nature of existence itself. When we look up at the night sky, we see a vast, awe-inspiring cosmos filled with stars, galaxies, and the mysteries of space. Yet, no matter how far we gaze, the ultimate fate of this grand expanse remains uncertain, and the universe's end is as inevitable as it is unfathomable. While we may understand much about the mechanics of stars, planets, and galaxies, we know remarkably little about how the universe will ultimately cease to exist, if indeed it ever does. The future of the cosmos is tied to forces beyond our comprehension, some of which are only beginning to be understood. However, scientists have put forth several theories that attempt to answer the question, how will the universe end? One possibility, which has been discussed for many years, is known as the Big Freeze. This scenario arises from the observation that the universe is expanding. Ever since the Big Bang, the universe has been steadily stretching out, with galaxies moving further apart from one another. This expansion is not slowing down as once expected, but is in fact accelerating due to a mysterious force called dark energy. Dark energy, which makes up roughly 68% of the universe, is thought to be responsible for this accelerated expansion. In a Big Freeze scenario, the universe will continue to expand at an ever-increasing rate, with galaxies, stars, and planets drifting further and further apart. As the universe expands, it will grow colder and darker, as the energy in the universe becomes more and more diluted. In the Big Freeze model, stars will eventually burn out as they exhaust their nuclear fuel. The process that powers stars, known as nuclear fusion, will slow down and stop as the supply of hydrogen diminishes. This will lead to the death of stars, with smaller stars turning into white dwarfs and larger stars collapsing into black holes or supernovae. Over time, even black holes will eventually run out of energy and evaporate, a process known as Hawking radiation. With no new stars being born and existing stars dying out, the universe will become a cold, dark expanse, with only remnants of the once bright galaxies left behind. Eventually, the universe will reach a state where no energy is available to power any processes, and all matter will be evenly distributed across space. This is the ultimate fate of the Big Freeze, a universe that has expanded so much that it has become a lifeless, frozen void. The Big Freeze is one of the most widely accepted theories about the end of the universe, but it's not the only possibility. Another scenario that has captured the imagination of scientists is known as the Big Crunch. In this theory, the expansion of the universe eventually slows down, halts, and then reverses. Instead of continuing to expand indefinitely, gravity would begin to pull everything back toward a central point. Galaxies, stars, and even entire clusters of galaxies would be drawn together by gravity, leading to a contraction of the universe. As everything collapses inward, temperatures would rise dramatically, and the universe would become an increasingly hot and dense singularity, similar to the state it was in just after the Big Bang. The Big Crunch would essentially be the opposite of the Big Bang, with the universe returning to a singularity before potentially collapsing into a final, catastrophic collapse. The Big Crunch hypothesis was initially proposed as a potential fate for the universe before the discovery of dark energy. The idea was that the combined gravitational pull of all the matter in the universe would eventually slow the expansion and cause it to reverse. However, the discovery of dark energy in the late 1990s led scientists to reconsider this theory, as dark energy appears to be pushing the universe apart at an accelerating rate, making a Big Crunch less likely. Still, some cosmologists suggest that if the amount of dark energy were to decrease or if the force were to behave differently in the future, a Big Crunch could become a possibility once again. But for now, this theory remains speculative and far less likely than the Big Freeze. A third potential fate for the universe is the Big Rip. The Big Rip is a more dramatic and violent end than the Big Freeze or the Big Crunch. In this scenario, the expansion of the universe doesn't just continue indefinitely, it accelerates to such an extreme rate that it rips apart everything in its path. This includes galaxies, stars, planets, and even atoms themselves. In a Big Rip scenario, dark energy doesn't just push galaxies apart, it accelerates to the point where it overcomes all other forces in the universe, including gravity and electromagnetism. The universe would reach a point where it begins to tear itself apart at the most fundamental level. First, galaxies would be pulled apart, then stars would be ripped from their orbits, and eventually, even the atoms that make up matter would be torn asunder. This scenario would culminate in a violent, cataclysmic end to everything, with the universe completely disintegrating into nothingness. While the Big Rip is a less widely accepted theory than the Big Freeze, it remains a possibility, particularly if the nature of dark energy changes in the future. Each of these scenarios, the Big Freeze, the Big Crunch, and the Big Rip, presents a different vision of the end of the universe, and each has profound implications for the future of everything. But there is yet another scenario that has captured the imagination of scientists: the possibility of a quantum death, or the end of the universe as a result of quantum fluctuations. In quantum mechanics, particles do not exist in a fixed state but instead exist in a superposition of different states until they are measured or observed. This phenomenon leads to the concept of quantum fluctuations, which are temporary, random changes in energy that occur even in the vacuum of space. Some scientists have speculated that the universe could be susceptible to a sudden and catastrophic quantum fluctuation, which could trigger a collapse of spacetime itself. This collapse would lead to the destruction of everything, effectively bringing about the end of the universe in an instant. While this idea is highly speculative and lacks empirical evidence, it remains a thought-provoking possibility in the realm of theoretical physics. One of the more philosophical implications of these scenarios is the idea that the universe's end might be tied to the concepts of entropy and the second law of thermodynamics. As we have discussed before, entropy is the measure of disorder in a system, and the second law of thermodynamics states that entropy always increases over time. This means that, in any closed system, disorder and chaos will eventually increase, leading to a state of maximum entropy. If we apply this principle to the universe, it suggests that the universe is doomed to a state of ultimate disorder, where all energy is evenly distributed and no more work can be done. Whether the universe ends in a Big Freeze, a Big Crunch, or some other fate, the inevitability of entropy suggests that the universe will eventually reach a point where all processes come to a halt, and time itself may cease to have meaning. What these scenarios also reveal is that the end of the universe is inextricably linked to the beginning of the universe. The Big Bang, the moment of creation, set the universe in motion, and now, billions of years later, the universe is heading toward its eventual end. This cyclical nature of creation and destruction has led some scientists and philosophers to wonder whether the universe will ever truly end. Could it be that the universe goes through infinite cycles of birth, death, and rebirth? Could the universe undergo a series of Big Bangs and Big Crunches, each one giving rise to a new universe, with no ultimate end but only endless cycles of cosmic transformation? Perhaps one of the most profound aspects of contemplating the end of the universe is the way it forces us to confront our own mortality. Just as stars are born and die, so too are we, living in a finite world with a limited time to experience all that it has to offer. Understanding that the universe itself will one day cease to exist helps us appreciate the preciousness of time and the fleeting nature of all things. It is a reminder that everything, from the smallest particle to the largest galaxy, is subject to the forces of time and entropy. In the face of such a grand and inevitable end, we are reminded of the fragility of life and the vast, unknowable nature of the cosmos. The end of the universe may be a distant, far-off event, but it serves as a reminder of our place in the cosmic order and the transient beauty of existence itself. The possibility of intelligent life existing elsewhere in the universe is one of the most captivating questions humanity has ever asked. For centuries we have wondered whether we are alone in the cosmos, or if there are other beings out there, beings with their own civilizations, technologies, and experiences of the universe. The search for extraterrestrial life has driven science and exploration, sparked the imaginations of countless individuals, and shaped our understanding of the universe. The question of whether intelligent life exists elsewhere is not just a matter of curiosity but one that touches on the fundamental nature of our existence. It forces us to question what it means to be human and to reconsider our place in the grand scheme of things. The search for extraterrestrial life is closely tied to the concept of the Fermi paradox. In 1950, physicist Enrico Fermi famously posed the question, "Where is everybody?" This seemingly simple query encapsulates a profound mystery. The universe is vast, billions of galaxies, each with billions of stars, many of which have planets that could potentially support life. Given these staggering numbers, the likelihood of other intelligent civilizations existing seems high. And yet, despite decades of searching, we have found no definitive evidence of extraterrestrial life. The Fermi paradox asks why, in a universe that should be teeming with life, we have not yet encountered any signs of it. One explanation for this paradox is the rare Earth hypothesis, which posits that the conditions required for life, let alone intelligent life, are so rare and specific that Earth is an exceptional case. According to this view, while microbial life may be relatively common in the universe, the emergence of complex life forms, and especially intelligent life, may be incredibly rare. Earth, with its unique combination of factors such as its distance from the Sun, the presence of liquid water, a stable climate and a protective atmosphere, may be a 1 in a billion fluke. If intelligent life is so dependent on such a specific set of circumstances, then it could be extremely rare, and we might be the only ones in the galaxy or even the universe with the capacity for advanced civilization. The rare Earth hypothesis contrasts with the more optimistic Copernican principle, which suggests that Earth is not special and that the conditions that allowed life to flourish here may be common throughout the universe. This principle argues that since Earth is not at the center of the universe, there is no reason to assume that we are the only planet capable of supporting intelligent life. The discovery of exoplanets, planets outside our solar system, has lent considerable weight to this view. As of now, thousands of exoplanets have been discovered, some of which are located in the habitable zone of their parent stars, where conditions might be right for liquid water to exist. The more we discover about these planets, the more it seems likely that Earth-like conditions could exist elsewhere in the universe. This raises the tantalizing possibility that other civilizations might be out there, waiting to be discovered. One of the key questions in the search for extraterrestrial life is whether other intelligent species are out there, and if so, why we haven't yet made contact. This question leads us to the concept of the Great Filter, a hypothetical explanation for the Fermi paradox. The Great Filter suggests that there is some stage in the development of intelligent life that is extraordinarily difficult to overcome. This filter could occur at any point in the evolutionary process, perhaps in the emergence of life itself, the transition from simple organisms to complex ones, the development of intelligence, or the rise of technological civilizations. The Great Filter hypothesis posits that the reason we have not encountered other intelligent civilizations is that most, if not all, of them fail to make it past this critical stage. It's possible that the path to becoming a technologically advanced civilization is fraught with insurmountable challenges that very few species are able to overcome. The fact that we have not yet discovered any evidence of extraterrestrial civilizations could be a sign that we, too, are in a very rare and fragile stage of development. If the Great Filter theory is correct, it would have profound implications for our future. If the filter lies behind us, meaning that the development of life and intelligence on Earth is the rare and difficult step, then humanity may be one of the few, if not the only, civilizations to ever exist in the universe. On the other hand, if the filter lies ahead of us, it would suggest that we are on the verge of facing some great existential challenge that could prevent us from ever becoming a spacefaring, technologically advanced species. This could involve anything from self-destruction through nuclear war or environmental collapse, to the inability to survive long enough to reach the technological capabilities needed to make contact with other civilizations. The search for extraterrestrial intelligence (SETI) has been an ongoing effort for decades, with scientists using radio telescopes and other instruments to scan the skies for signals from other civilizations. Despite this extensive search, no definitive signals have been found, which only deepens the mystery. However, some researchers suggest that the lack of contact may not be due to the absence of intelligent life, but rather to the fact that extraterrestrial civilizations may be intentionally avoiding us. This idea is known as the zoo hypothesis. According to this theory, advanced extraterrestrial civilizations are aware of humanity's existence but have chosen not to make contact, perhaps for ethical or observational reasons. They might view us as a zoo, a species in its infancy that is not yet ready for contact with more advanced civilizations. In this view, extraterrestrial civilizations could be monitoring us from a distance, much like scientists observe animals in the wild, but they refrain from interfering with our development. Alternatively, there is the possibility that extraterrestrial civilizations may not even be using the same forms of communication that we do. We are currently searching for radio signals or other electromagnetic signals, assuming that extraterrestrial life would communicate in a similar manner to us. However, it is entirely possible that advanced civilizations have developed completely different forms of communication that we are not capable of detecting or understanding. They may be using technologies that are so far beyond our own that we simply have no way of recognizing them. This is a possibility that is often overlooked but deserves consideration, as it challenges our assumptions about what intelligent communication might look like. Another intriguing possibility is that intelligent extraterrestrial civilizations could be so vastly different from us that they would be unrecognizable to our senses. What if their consciousnesses or forms of existence are not based on the same biological principles as ours? Perhaps they do not even inhabit physical bodies, but exist as pure energy, or in a form that we can neither comprehend nor detect. If this is the case, then our search for extraterrestrial life might be limited by the constraints of our own biology and perception. We may be searching for life forms based on carbon and water, but what if life can exist in forms entirely alien to our understanding? The search for extraterrestrial life also leads us to consider the implications of making contact. What would happen if we did discover intelligent extraterrestrial civilizations? Would they be benevolent, indifferent, or hostile? The vast distances between stars and the challenges of interstellar communication and travel suggest that the chances of direct contact with extraterrestrial civilizations may be slim. However, if contact were made, it could have profound effects on human society. The discovery of intelligent extraterrestrial life would challenge our most fundamental assumptions about the nature of life, consciousness, and our place in the universe. It could force us to rethink what it means to be human and how we relate to other forms of intelligence. In the grander scheme of things, the question of extraterrestrial life touches on existential themes. Are we truly alone in the universe, or are we just one of many civilizations scattered across the cosmos? The answer to this question could reshape our understanding of the universe and our role in it. If intelligent life is out there, it could suggest that the universe is far more interconnected and complex than we could ever imagine. On the other hand, if we are truly alone, it could make our existence all the more unique and precious. In the end, the search for extraterrestrial life is not just about finding other beings out there, it's about exploring the very nature of existence itself. It challenges us to look beyond our own small corner of the cosmos and to consider the larger, more profound mysteries of life, intelligence, and the universe. Whether or not we ever make contact with extraterrestrial civilizations, the search for life beyond Earth will continue to inspire humanity to reach for the stars and to ponder the ultimate question: are we truly alone in the vast expanse of the universe? As we attempt to fathom the future of everything in the universe, one of the most profound and perplexing aspects to consider is the nature of consciousness. Consciousness is the very fabric of our subjective experience, the lens through which we perceive the world around us, our thoughts, emotions, and sense of self. It is the cornerstone of everything we understand about what it means to be alive. Yet, despite its central role in our existence, consciousness remains one of the greatest mysteries of science and philosophy. We know that consciousness exists, but we have only the vaguest understanding of what it actually is or how it arises. Could consciousness be something more than a byproduct of the brain? Is it possible that consciousness exists beyond the individual, perhaps stretching across time, space, or even the universe itself? These are the questions that continue to intrigue and confound researchers, philosophers, and thinkers alike. The conventional view of consciousness, as understood by most scientists, is that it is a product of the brain's complex neural activity. According to this view, consciousness arises from the interactions of neurons, electrical impulses, and biochemical processes within the brain. The brain is the central organ that processes sensory input, generates thoughts, and controls actions. As such, consciousness is seen as an emergent property of this complex network of activity. This view aligns with the materialist perspective, which holds that everything in the universe, including consciousness, can ultimately be explained by physical processes and interactions. From this standpoint, Consciousness is no more than a sophisticated computational function of the brain, one that emerges as a result of evolution and the increasing complexity of neural networks. However, despite the widespread acceptance of this materialist perspective, consciousness remains stubbornly elusive. The hard problem of consciousness, as philosopher David Chalmers famously coined it, refers to the difficulty of explaining why and how subjective experience arises from physical processes in the brain. While scientists can study the brain's activity and identify correlations between neural states and conscious experiences, they are still unable to answer the fundamental question: why does any of this feel like something? In other words, why does the firing of neurons and the flow of electrical signals result in the rich tapestry of inner experience, the colors, sounds, emotions, and thoughts that constitute our consciousness? This gap between the physical processes of the brain and the subjective nature of experience is what makes consciousness so challenging to understand. One of the most intriguing aspects of consciousness is its apparent connection to the concept of self-awareness. We are not merely passive observers of the world around us, we are also aware of ourselves as beings who are conscious. We have a sense of I, a sense of individuality and selfhood that persists through time. This self-awareness allows us to reflect on our thoughts, emotions, and actions, to make decisions based on past experiences, and to contemplate our own existence. But how does this sense of self arise from the neural activity in the brain? If consciousness is simply a product of the brain, how is it that we can become aware of ourselves and our own consciousness? This question has led some philosophers and scientists to suggest that consciousness may not be a local phenomenon confined to the brain, but rather something that exists on a more universal scale, stretching beyond the individual and into the very fabric of reality itself. One possibility that has gained traction in recent years is the idea that consciousness is a fundamental aspect of the universe, akin to space, time, and matter. This is known as panpsychism, the belief that consciousness is not something that emerges solely from complex brains but is instead a fundamental property of all matter. In this view, consciousness is not something that exists only in humans or animals, but is present to some degree in all things, whether they be atoms, molecules, or even the fundamental forces of nature. While this may seem like an outlandish idea, panpsychism has roots in the ancient philosophies of animism and idealism, and it has gained renewed attention in modern philosophy and science. Some proponents of panpsychism suggest that just as all matter has mass and energy, all matter also has some degree of consciousness, however rudimentary it may be. This could mean that the universe itself is imbued with a form of awareness or experience, and that consciousness is woven into the very fabric of reality. If consciousness is indeed a fundamental property of the universe, this raises profound questions about the nature of existence and the future of everything. Could consciousness be the key to understanding the universe itself? Could it be that the universe is not just a collection of inanimate objects but a vast, interconnected web of conscious experience? Some theories suggest that the universe is a vast, self-organizing system of consciousness, with individual beings and minds acting as nodes in a larger cosmic consciousness. In this view, everything in the universe, from the smallest subatomic particle to the largest galaxy, could be seen as part of a unified, conscious whole. This would mean that consciousness is not just something that resides within individual beings, but is a pervasive force that connects all of existence. One of the most fascinating implications of this view is the possibility that consciousness could extend beyond the limits of the individual mind. If consciousness is indeed a universal property of matter, it might be possible for consciousness to transcend the boundaries of space and time. Some theories suggest that consciousness could exist on a higher, non-local level, beyond the confines of the physical brain. In this view, individual consciousness would not be tied to a specific brain or body, but could be part of a larger, interconnected network of consciousness that spans the entire universe. This could imply that consciousness is not merely a transient, individual experience but a continuous and eternal force that exists across time and space. If this is the case, then the death of the individual may not mark the end of consciousness itself. Instead, consciousness could persist in some form, possibly even transcending the limitations of physical existence. The idea of non-local consciousness also opens up the possibility of what some might consider cosmic consciousness. In this vision, individual minds are seen as temporary manifestations of a greater, universal consciousness that exists beyond time and space. This would suggest that the universe itself is conscious in some way, and that individual consciousnesses are merely expressions of this larger, cosmic mind. This view has been explored by mystics, philosophers, and scientists alike, and it raises the possibility that our current understanding of consciousness is just the beginning of a deeper, more profound reality. If the universe is indeed a conscious entity, then the future of everything might not simply be a series of random events governed by physical laws, but the unfolding of a cosmic process driven by awareness, intelligence, and intentionality. As we contemplate the future of consciousness, one of the most pressing questions is how technological advancements might affect the nature of our conscious experience. With the rapid development of artificial intelligence, AI, neuroscience, and brain-computer interfaces, the boundaries between human consciousness and technology are becoming increasingly blurred. Could we one day upload our consciousness into a machine, allowing us to live forever in digital form? Could AI achieve a form of consciousness on its own? And if so, what would that mean for the future of life and intelligence in the universe? These questions touch on both the promise and the peril of our technological future. While the prospect of enhancing or even transcending our biological limitations is tantalizing, it also raises profound ethical, philosophical, and existential questions about the nature of consciousness, identity, and what it means to be human. The potential for merging human consciousness with machines also raises the possibility of creating a collective consciousness, a shared, interconnected mind that spans across individuals, cultures, and even species. In this scenario, consciousness could become a communal, shared experience, where individuals are no longer isolated but are instead connected to one another on a deeper, more profound level. This could radically alter the future of everything, leading to new forms of social organization, collaboration, and understanding. However, it could also pose significant challenges, as the boundaries between individual identity and collective consciousness become increasingly blurred. Could a shared consciousness lead to greater harmony and understanding, or would it result in the loss of individuality and freedom? In the grand scheme of things, the future of consciousness is deeply intertwined with the future of the universe itself. If consciousness is indeed a fundamental property of the universe, then its evolution could be just as important as the evolution of galaxies, stars, and planets. The unfolding of consciousness, whether on a universal or individual scale, may hold the key to understanding the deepest mysteries of existence. As we continue to explore the nature of consciousness, we may find that the future of everything is not just about the material universe, but also about the profound, interconnected web of awareness that shapes our experience of reality. Whether consciousness is something that arises from the brain, exists beyond the individual, or is a fundamental aspect of the cosmos itself, its future will undoubtedly shape the ultimate fate of all things. The concept of time has long been one of the most perplexing and enigmatic aspects of our existence. We experience time as an unbroken, ever-flowing stream that moves from the past, through the present, and into the future. Yet, despite the seemingly straightforward nature of time in our daily lives, it remains one of the most profound mysteries in both science and philosophy. What is time really? Is it an illusion, a human construct, or a fundamental feature of the universe itself? How does time relate to space, matter, and energy, and can we ever truly understand its nature? The answers to these questions hold the key not only to understanding the flow of our own lives but to unlocking the deepest secrets of the universe. One of the earliest and most influential theories about time was introduced by Sir Isaac Newton, who posited that time was an absolute, unchanging entity, independent of the events that occurred within it. In this view, time was a continuous, linear progression that ticked away uniformly, regardless of the motion or existence of objects in the universe. This absolute time was central to Newtonian mechanics and provided a framework for understanding the laws of physics. According to this perspective, time could be measured, predicted, and observed in the same way that space could be mapped. Time was simply a backdrop to the universe, an empty stage upon which the events of the cosmos unfolded. However, in the early 20th century, the advent of Albert Einstein's theory of relativity fundamentally challenged this view of time. Einstein proposed that time, rather than being absolute, is relative. It can stretch, contract, and bend depending on the speed at which an object is moving and the strength of gravitational fields it is subject to. According to the theory of special relativity, time slows down for objects that are moving at speeds approaching the speed of light. This phenomenon, known as time dilation, has been experimentally confirmed through observations of atomic clocks on fast-moving airplanes and satellites. In the theory of general relativity, Einstein expanded on this idea, showing that time is also affected by the curvature of space caused by massive objects like stars and planets. The more massive an object, the stronger its gravitational field, and the more time is distorted in its vicinity. Time, it turns out, is not a constant, immutable flow but something that is influenced by the very fabric of space and the forces within it. This revelation about the relativity of time has profound implications for how we understand the universe. For example, the concept of time dilation has practical consequences for space travel. If we were able to travel close to the speed of light, time for the travelers would slow down relative to people remaining on Earth. This means that astronauts could theoretically experience time at a different rate than people on Earth, leading to a form of time travel into the future. While this is not the time travel we often see in science fiction, where characters move backward or forward in time at will, it is a real and scientifically grounded phenomenon. As we push the boundaries of space exploration, time dilation could become an important factor in how we understand long-duration space missions and the aging of astronauts. In addition to the relativity of time, another fascinating aspect of time is its directionality, what is often called the arrow of time. While the laws of physics themselves are mostly time-symmetric, meaning that they don't distinguish between past and future, we experience time as having a clear direction, from past to present to future. This is in part due to the second law of thermodynamics, which states that the entropy or disorder of an isolated system tends to increase over time. In simpler terms, this means that systems naturally evolve from states of lower entropy, more order, to states of higher entropy, less order. This increase in entropy gives rise to the perception of time moving in one direction, from a more ordered past to a more disordered future. The concept of entropy also ties into our understanding of time's passage, as we see the world around us becoming increasingly disordered over time, from the aging of living organisms to the eventual decay of stars and galaxies. Time seems to be linked to the inevitable march of entropy toward its maximum state. Yet, the question of why time has a direction at all remains one of the biggest unsolved mysteries in physics. Why does time flow in one direction and not the other? Why don't we observe time running backward, with events unfolding in reverse order? This question remains at the heart of many debates in cosmology and the philosophy of time. Some theories suggest that the directionality of time is linked to the initial conditions of the universe, the Big Bang. In the very early moments of the universe's existence, conditions were incredibly ordered, with matter and energy tightly packed into a singularity. As the universe expanded, the entropy of the system began to increase, setting the stage for the passage of time in one direction. But this still doesn't explain why time had to begin with such a low level of entropy in the first place. The origin of time's arrow remains a mystery. The relationship between time and the universe's structure is another area of intense study. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and zero volume, approximately 13.8 billion years ago. From that moment of inception, time and space themselves began to expand, and the universe began its complex evolution. This suggests that time, in some sense, began with the universe itself. Time is not something that exists independently of the cosmos, but something that arose alongside it. If the universe is finite, then time may have a beginning and an end. But what happens when we approach the end of the universe? Could time come to an end, or will it continue to unfold in some form, regardless of the fate of the universe? One theory that has gained increasing attention in recent years is the possibility that time may not be a fundamental aspect of reality at all. Some researchers propose that time, along with space, could emerge from deeper, more fundamental principles of physics. This idea, known as emergent time, suggests that time could be a phenomenon that arises from the interactions of more fundamental entities, rather than a pre-existing feature of the universe. This would mean that time, as we experience it, is not a fundamental aspect of reality but a derived concept that emerges from the quantum interactions of particles. If this is the case, the nature of time could be far more complex and strange than we currently understand. Another intriguing possibility is that time, as we experience it, might be an illusion, a product of the way our minds process sensory information and construct narratives about the world. According to this view, time is not an objective feature of the universe, but a mental construct that helps us make sense of the continuous flow of events. This is a perspective that has been explored by philosophers for centuries, most notably by Immanuel Kant, who argued that time, along with space, is a category of the mind that shapes our perception of reality. From this standpoint, time would be a feature of our consciousness rather than an intrinsic property of the external world. This raises profound questions about the relationship between subjective experience and objective reality. Is time something that exists, out there, independent of our perceptions, or is it simply a way for our minds to organize the world? As we delve into the future of everything, the role of time will undoubtedly continue to be a central theme. The fate of the universe, from its potential end in a big freeze, big rip, or other scenarios, will be inextricably linked to the nature of time itself. If time continues to flow as we understand it, it will likely carry the universe to its inevitable conclusion, whether that is the slow death of all stars or the disintegration of matter itself. However, if time is not a constant, if it can bend, stretch, or even cease to exist, the very future of the universe could be radically different from what we expect. Could time itself run out? Or could it collapse in on itself, marking the end of all processes? These questions challenge our deepest assumptions about reality and force us to confront the possibility that our current understanding of time may be only the beginning of a much deeper and more mysterious truth. Theories about time also hold profound implications for the way we understand our own existence. If time is not a linear, unidirectional flow but something more fluid, more dynamic, then our entire concept of life, death, and experience could be transformed. Could the past, present, and future be interconnected in ways we cannot yet comprehend? Could our experience of time be a limited perspective on a much larger, timeless reality? As we explore these questions, we are reminded that time is not just a scientific concept, but a deeply philosophical one. One that speaks to our understanding of the cosmos and our place within it. Whether time is a fundamental feature of the universe or a product of our minds, its mysteries continue to inspire wonder, awe, and profound reflection. In considering the fate of the universe, one of the most intriguing aspects that we must address is the role of dark matter and dark energy. These mysterious substances make up roughly 95% of the total mass energy content of the universe, yet they remain largely invisible and undetectable by traditional means. While the visible matter, the stars, planets, and galaxies that we can see, constitutes only about 5% of the universe's mass energy content, dark matter and dark energy govern the large-scale structure and evolution of the cosmos in ways that we are only beginning to understand. The discovery of these phenomena has forced a complete rethinking of our understanding of the universe's composition, its future, and the forces that shape its destiny. Dark matter, first hypothesized in the 1930s by the Swiss astronomer Fritz Zwicky, is thought to account for roughly 27% of the universe's total mass energy content. Unlike ordinary matter, which interacts with light and electromagnetic radiation, dark matter does not emit, absorb, or reflect light, making it completely invisible to our current observational instruments. This means that dark matter cannot be detected directly through electromagnetic radiation, such as visible light, X-rays, or radio waves. Instead, scientists infer the presence of dark matter based on its gravitational effects on visible matter. For instance, when astronomers observe the motion of galaxies and galaxy clusters, they find that the gravitational pull exerted by the visible matter, such as stars and gas, does not seem to be enough to account for the observed motions. This discrepancy suggests that there is an unseen mass, dark matter, present, influencing the behavior of galaxies and clusters at a large scale. One of the key pieces of evidence for dark matter comes from the study of galaxy rotation curves. Galaxies are observed to rotate at a rate that cannot be explained by the gravitational effects of the visible matter alone. If only the stars, gas, and dust were influencing the galaxy's rotation, the outer stars would be moving much slower than they actually are. Instead, the stars in the outer regions of galaxies move at roughly the same speed as those closer to the center. This suggests that there is a large, invisible mass surrounding these galaxies, exerting additional gravitational pull. This unseen mass is what we call dark matter. Despite its central role in the structure of galaxies, the exact nature of dark matter remains a mystery. Scientists have proposed several candidates for what dark matter could be, the most prominent of which are weakly interacting massive particles, WIMPs. These hypothetical particles would interact with ordinary matter only through gravity and possibly the weak nuclear force, making them extremely difficult to detect. Other candidates include axions, which are light particles that could also contribute to the mysterious dark matter. Experiments are ongoing to detect dark matter particles, but so far no direct evidence has been found, and it remains one of the greatest challenges in modern physics. Dark matter is not just a mystery because of its invisibility, it also plays a critical role in the overall structure of the universe. Without dark matter, galaxies would not have the necessary gravitational pull to hold together. It also helps explain the observed distribution of galaxies throughout the cosmos. In the early universe, dark matter acted as a sort of scaffolding, providing the gravitational foundation around which normal matter could accumulate to form galaxies and clusters of galaxies. Without dark matter, the universe would look vastly different, with galaxies likely being far less stable and the overall structure of the cosmos far more chaotic. But dark matter alone does not explain the universe's large-scale behavior. Enter dark energy, an even more mysterious force that is thought to account for approximately 68% of the universe's mass energy content. Dark energy was first proposed in the late 1990s to explain an unexpected observation. The expansion of the universe is accelerating, rather than slowing down as had been previously assumed. According to traditional models of cosmology, the gravitational pull of all the matter in the universe should slow the expansion over time. However, measurements of distant supernovae revealed that the rate of expansion is actually increasing, suggesting the presence of a repulsive force that counteracts gravity. This force is what we call dark energy. Unlike dark matter, which exerts an attractive gravitational force and helps to bind galaxies and clusters together, dark energy works in the opposite direction. It is thought to have a repulsive effect, causing the fabric of spacetime to stretch and accelerate the expansion of the universe. The discovery of dark energy was a groundbreaking moment in cosmology, as it fundamentally altered our understanding of the fate of the universe. If dark energy continues to drive the expansion of the universe at an accelerating rate, it could lead to a future in which galaxies, stars, and even atoms are stretched apart beyond recognition. One of the most profound implications of dark energy is that it may ultimately determine the fate of the universe. If dark energy continues to dominate the universe's evolution, it could lead to what is known as the Big Freeze. In this scenario, the universe would continue to expand at an accelerating rate, eventually causing galaxies to drift so far apart that the observable universe would shrink to an isolated, dark void. Stars would burn out, and the energy available for sustaining life would be diluted to the point where the universe would be a cold, lifeless place. The Big Freeze is one of the leading theories for the ultimate fate of the universe, driven in large part by the influence of dark energy. Another possible fate of the universe, driven by dark energy, is the Big Rip. In this scenario, the expansion of the universe would continue to accelerate at an increasingly rapid pace, eventually overpowering all the forces that hold matter together. Galaxies would be torn apart first, followed by stars, planets, and eventually atoms themselves. In the final moments of the Big Rip, even the very fabric of spacetime would be stretched to the point of rupture. While the Big Rip remains a speculative scenario, it serves as a reminder of the incredible power that dark energy exerts on the universe's future. The role of dark matter and dark energy in shaping the universe's fate forces us to reconsider some of the most fundamental questions in cosmology. If we cannot detect dark matter or dark energy directly, how can we know they exist? Our understanding of these substances relies on indirect evidence: gravitational effects, the motion of galaxies, the acceleration of the universe's expansion. But we have yet to identify the actual particles or forces that make up dark matter and dark energy. This lack of direct detection means that dark matter and dark energy remain largely theoretical, and our understanding of them is constantly evolving. One of the key challenges in studying dark matter and dark energy is that they are so different from the ordinary matter that we are familiar with. Ordinary matter interacts with light and electromagnetic radiation, making it detectable through telescopes and other instruments. Dark matter, on the other hand, interacts only through gravity and possibly the weak nuclear force, making it nearly impossible to detect. Dark energy, meanwhile, is even more elusive as it does not interact with matter in any conventional way. It only affects the expansion of space itself. As our tools and technologies improve, scientists hope to unlock the secrets of dark matter and dark energy. New experiments and observatories such as the Large Hadron Collider, LHC, and the James Webb Space Telescope are designed to probe the fundamental forces and particles that govern the universe. Advances in particle physics, cosmology, and astronomy may one day provide a clearer picture of these elusive substances and their roles in shaping the future of the cosmos. In the meantime, the search for dark matter and dark energy continues to be one of the most exciting and challenging endeavors in modern science. These mysterious forces hold the key to understanding not just the future of the universe, but also its past. How did dark matter and dark energy come to be, and how have they influenced the evolution of the cosmos? What role do they play in the fundamental laws of nature, and how can we incorporate them into our broader understanding of the universe's creation and ultimate fate? As we continue to explore these questions, it becomes clear that dark matter and dark energy are not just the subjects of scientific curiosity, but also a profound reminder of the limits of human knowledge. In many ways, they represent the unknown frontiers of our understanding, the edges of our intellectual horizon. As we look to the future, we are reminded that the universe is far more complex, mysterious, and awe-inspiring than we could have ever imagined. Dark matter and dark energy are the invisible forces that shape the universe, and their influence will continue to guide the fate of everything that exists.